Okay, so again, this looks very familiar to when we did our series circuit. Normally you'll get a circuit where you have some information that's given, but you are missing some variables. So you have to use your relationship information to realize what how to figure out the missing pieces. Okay, so we have some, we can, first of all, you have to look at this and say, well, is this series or is this parallel? So when you follow this along, right, here is our fork in the road. So there's 1, 2, 3. Over here, they all come back together again, right, if you notice that. So over here, when you're looking at this, this information can sometimes be over here. So let's say instead of the current right here, maybe they gave current over on this side. You have to understand that anywhere where it is on the same line, the current is the same. So even if they gave the current even way over here, it would still be the 15 amps. Okay, so let's figure this out. So we have, let's do voltage first since that's the easiest one when we're looking at parallel. So we have 24 volts. So every line that is traveled on only has one load. So that means that each of these is also 24 volts. Right? 24 volts, 24 volts. The other thing we have to consider now is we have to look at current. So the total current is 15 amps, and we know that one of them is 9 amps. So now you cannot really make an assumption that these two are going to be the same number. However, in this particular case, you actually can. Now, the reason why is because if you remember, you can use Ohm's law to solve for the missing information. So because I have R and V, I could solve for I that way, right? I is equal to V times, pardon me, V is equal to I times R. What am I saying? V is equal to I times R. So I would be equal to V over R. So we actually could solve for this using Ohm's law. So let's do that. So if we have our voltage is 24 divided by 8, that means that this is 3 amps. Now the reason why I said that these are going to be the same is because if you look, the resistance is equal and so is the voltage. So actually I3 is also 3 amps. Okay, now this should make sense. If we did this correctly, they should add up to 15 amps. So 3 plus 9 is 12. 12 plus 3 is 15. So there we go. So now for resistance, we can actually do this a few ways. Okay, I'm going to show you using the long way that we just learned on at the end of the last part. But another, not really a sneaky way, but you can solve for resistance using Ohm's law. R is going to be equal to V over I. So because we have I and we have V, we can actually solve for it using this method. And that's completely valid. Okay, but I'm just going to show you again how to set this up if you wanted to do it this way, or you might be stuck doing it this way because you may not have any other information. You might not have V and I. Do not rely on this. You need to be comfortable using the long way as well. So we have 1 over R1 plus 1 over R2 plus 1 over R3 because there's 3 in this case. So this is going to be 1 over 8 ohms plus 1 over 2.7 ohms plus 1 over 8 ohms. Oh my goodness, that was not great. Ohms. Okay, so we're going to divide this out. We're going to do 1 divided by 8, which is 0.125 plus 1 divided by 2.7, which is 0.37, plus, this is going to be the same answer, 0.125. Okay, so 1 over RS is equal to, let's add these all up, 0.125 plus 0.37 plus 0.125 gives us 0.62. So now we're going to swap these locations. So RS is going to be equal to 1 over 0.62, which gives us an answer of 1.61, and that is ohms. Okay. Now remember, anytime you are dealing with these series circuits or parallel circuits where you have to input the numbers, always keep it to 2 decimal places. You're not going to use significant digits here. It's the only time where significant digits is when we're doing our word problems with grasp. Here we are simply going to do 2 decimal places. And when you have your test and your quiz or whatever the case is, I will remind you of that to report your answer to 2 decimals. Okay, so now that's basically the whole lesson. We're going to practice. So pause the video. So same with everything else. You're just going to input, similar to what we did with series, you're going to input the missing values. So pause the video, give this a try, and then we'll see how you do. Okay, so for your voltage, right, because this is in parallel, that means that this one here that we're solving for is also 9 volts. We have current, so the total is 12 amps. So we have 6 and 3. That means our other current must also be 3. Right, so that way it adds up to 12. Okay, pause this video, give this one a try. You're looking for VS and one of the currents. Okay, so VS should be 6 volts, right? Because we know that each of these resistors have 6 volts, which means this must also be 6 volts. Our current has to add up to 15. So 15 minus 9 gives us 6 amps. Okay, so give this one a try. We're solving for R3 here. Now the situation, let me set this up so you can do this properly. Okay, so this is very similar, except you want 1 over R3 to be by itself. So what that means is you want those other items to be on the other side. So basically it's going to be 1 over RT minus 1 over R1, because remember it's the opposite function when it goes over, minus 1 over R2 is equal to 1 over R3. But the situation, the setup is the same. You're going to plug in the values, divide them out, and then do the swap at the end. Okay, give this a try. Okay, so this is 1 over 0.82 ohms minus 1 over 5.5 ohms minus 1 over 8.2 ohms is equal to 1 over R3. So when we divide this out, 1 divided by 0.82 gives us 1.2195 minus 1 divided by 5.5, 0.182 minus 1 divided by 8.2, which is 0.122. Okay, and we'll do the calculations here. 1.2195 minus 0.182 minus 0.122. We get 0.9155 is equal to 1 over R3. We're going to swap the locations. So R3 is equal to 1 over 0.9155. And when we divide that out, we get 1.09 ohms. Okay, so this method works no matter which resistance you are looking for. So if you're looking for R1, that means you would move over R2 and R3. If you were looking for R2, you move over 1 and 3, right? So you always move over whatever you are not trying to solve for. You want the one that you are trying to solve for to be the only thing on that side. Okay, so give this one a try. You're looking for the missing current. Okay. So to solve for this, right, take your total and you subtract the other two. Right? So 12.5 minus 2.5 minus 4.0 gives us a value of 6 amps. Okay, we're looking for the total current in this case. This should be pretty straightforward. Okay, so we have 2 plus 1 is 3 plus 4, which gives us 7. Okay, now that's the end of the parallel circuit. So just to go over some of the comparisons, right? So in a series circuit, current is always the same. Parallel is additive. So on those different forks, those different pathways, they should add up to the pathway when everything is together. Potential difference is literally quite the opposite. So over here, we have voltage that is additive in series, and they are the same when they are in parallel. Resistance is additive in a series circuit, and we have Kirchhoff's law when we're dealing with parallel circuits. Now, if we're comparing bulbs and the brightness of the bulbs, with every bulb you add in a series circuit, the light that's produced actually becomes dimmer and dimmer. So just to kind of bring that point home, let's say we had a circuit with 1. So let's say the voltage was 5 volts. If you have only one light bulb, that means that bulb is giving off 5 volts worth of energy. If I take the same battery, but add another light bulb, that means that this 5 volts is now going to be split. Because remember, the battery is the total voltage and it's additive. So when you add in more loads, the amount of energy per load is actually lessened because they're only on one pathway, the electrons have to spend energy at each load. So if I were to add a third one in here, the energy would become even less. But because parallel circuits do not have to share the voltage, every load has its own. So let's say we added another, let's make this a parallel circuit. This would also get the same voltage because they're not sharing the same electrons. So what ends up happening is a parallel circuit, the bulbs, the loads would all have exactly the same brightness. Okay, in terms of switches, let me clear this up. Okay, so for switches, where the switch is located is actually very important. Okay, now for a series circuit, it actually doesn't matter. So if I have a switch here, or if I have my switch over here, if my switch is open, okay, so let's imagine that's open, because the electrons are all flowing in one pathway, as soon as there is a gap in that path, the whole thing would turn off. No electrons would be flowing. So one switch would really control all the bulbs being on or all of them being off. But if you have a parallel circuit, okay, where the switch is located really will matter. So if I put a switch on this line and a switch on this line, that means that this switch is controlling only this line, this pathway. This switch is controlling this pathway. So let's say this is off because I opened up this switch. The electrons can still flow on this closed switch. It's only the open path that cannot go in, that cannot have electrons flowing. So this allows us to have the ability of controlling one line or one pathway at a time. This is actually how your house works. When you turn on a switch, the whole house doesn't turn on. You're turning on one light or one item. Okay, we'll continue this in the next part.